Hello, this is part two of our discussion of understanding variation. In part one, recall I talked about the two types of process variation, common cause and special cause, and I illustrated the concept of common cause variation using the quincunx, where we drop the beads and the beads hit various pins and take different paths. And as a result, over a lot of drops, we see a whole distribution of finding final landing locations. And I mentioned that the pins in the quincunx represented common cause variation because they're always present. I also discussed the issue of tampering. That is making superficial adjustments to a process based on the outputs, trying to improve the process. Tampering is basically reacting to noise in the system. In other words, instead of getting to the fundamental causes of variation, one is constantly in a reactionary mode. Well, in this part two section, I just want to elaborate a bit more on the classification of variation. And again, I won't cover every slide in the section, and I do hope you'll go through the slides and read them in detail. So Deming, and I think I'll put this on slideshow at this point. Okay. As I said, Deming, and actually this goes back to Shewhart 100 years ago, said the variation we observe in a process, again, it could be manufacturing or service, can be common cause and special cause. And I will point out these days that we often also talk about a third type of variation we call systematic, and that would be something like a seasonal trend in sales. So many companies sell products or services, and you see a pattern that is consistent over time. It's not random, so it's not common cause, but the pattern is always there, the systematic pattern, so we make a third category we call systematic. Again, common cause variation, don't overthink it. It's nothing more than the inherent variation. The sources are always present. Think the pins in the quincunx. They're always at work, always impacting the path that the bead follows before it gets to its final location when it's dropped. So if you have common cause variation, it's inherent, it's always present. And something that's important, it also means it's predictable over time. The total amount of variation is predictable. So for the quincunx, having dropped a lot of beads, I know that almost all of them fall between 10 and 22. I can't tell you on any one drop where a bead will fall. I can just tell you over time they'll be between 10 and 22. Okay. So if there's common cause variation only in the process, we say it's in control or stable, and the total amount of variation over time is predictable. Now, those are good things, but that doesn't mean the process doesn't need improvement. It just means at least we understand the variation. Okay. So again, I said a process with only common cause variation has a predictable amount of variation over time because its behavior is stable. Okay. And I'm showing something we'll talk about later in the course called a control chart, but for now it's just a plot over time. And what you're looking at is this is a machine that grinds piston rings to their final diameter. And over some 200 samples, we've measured the diameter and we've plotted it. Notice there's lots of variation as you look across the plot, but you know what? It's all inherent or natural. So basically what are called these control limits on this chart, What they tell us is these are the bounds of common cause variation. As long as the piston rings are falling within these bounds, just like we saw with the virtual quincunx, everything's fine. Process is stable, and all of this variation we're seeing is just common cause or inherent, or some people like to say just noise. Whatever's causing this variation, it's always present, and this is natural. So since this process is stable, I can make statements about the amount of variation we'll see in the process. And we're saying it's about 70.4.7 to about 75.3, and these are in millimeters. Not that that really matters. Okay, so that's what a process would look like over time, or a service if it's in control, if it's stable. Only common cause variation is present. Okay, and if I make a histogram, basically I'm showing you the pattern of variation. Again, we call this a distribution. So this is a mound-shaped distribution, and you can see that overall we tend to be around 75 millimeters, but we can have a lot of variation around that. By the way, 75 is the target. And again, you can see for the most part, we're around the target, but the natural variation, some of the piston rings will be actually some distance from the target. Okay, so there are all kinds of sources of common cause variation. Again, the key is these are things that are always present. They're just inherent to the process. So, again, if you want to use the example of traveling to work, there are definitely things that happen every day. They're just a natural part of your journey that cause your times to vary. Again, something that is not common cause would be like suddenly the train derails, or you get a flat tire, things that are not inherent. But other things like natural ebb and flow of traffic and the general road conditions, those would all be things that you're dealing with every day. Okay. So remember, from the rule of the funnel, if a process is stable, that is, only inherent or common cause variation is present. If you tamper with it, that is, you try to improve it by reacting to the outputs and not really understanding cause and effect, then you'll only make the situation worse. And this is important because, as I said, tampering is the #1 cause of excessive variation in a process. You need to get, in a Six Sigma project, you need to get to a stable process before you can really improve it. And Deming made a statement. He said that about 94% of the variation is in the system. He meant common cause. Now, I don't know if it's 94, 90%. The point being, most of the variation you see in a process over time is inherent. It's common cause. The goal of Six Sigma is to go after that 94%. We take it as a given that we'll do something about special cause variation. And by the way, special cause variation may only be a small percentage of the total variation, but when it occurs, it can be catastrophic. It can be a major disruption. Just like you're traveling to work and there's a very bad accident, a highly unusual event, even though it will only occur very rarely, when it does, it's very disruptive. Or the train derails, again, something very unusual, that we would call a special cause. That's not inherent to the system, and when it happens, even though it's infrequent, it can be catastrophic. So it is important to understand special cause variation and do something about it, and that is prevent it. So special causes, in fact, I like to call it large scale variation, because when a special cause occurs, frequently it has a big effect. And if you're carefully observing a process, you can often catch it. Okay. So when we talk about special causes, they are not part of the system. It's something external and they're unpredictable. So a process in which special cause variation occurs is unpredictable. In other words, in that funnel, if I keep moving the funnel position around all the time, the total amount of variation you'll see in that funnel is no longer predictable. Why? Because I'm tampering. I'm actually moving the funnel about. So for common cause variation, I said almost all the drops land from 10 to 22. If I start moving the funnel around, all bets are off. And I can't predict the variation because every time I tamper, I may tamper in a different way. So special causes of variation are important. We need to catch them and we need to protect the system against them or find a way to eliminate them. Okay, and that is an important part early on of a Six Sigma project. If it's not stable, we need to know it and we need to catch the sources. And later on, we're going to talk about statistical process control, which was invented by Walter Shewhart as a way for people to catch special cause variation when it happens in their process. But for now, we're just going to discuss special cause variation. We're not going to get into the specific tools to try to detect it and eliminate it. Okay. So there can be many, many reasons for special cause variation. Power fluctuations, damage that's done to equipment, updates to software that go awry. It's endless, but the point is it's something that is not inherent. It's something that externally has been done to the process that has upset it. Okay. So as I said, large scale, the special cause is usually large scale. Unlike the common causes of variation, they're always at work and more or less they're canceling each other out. So on average, the process stays at some level. But once you have tampering, there's nothing in the system to offset tampering. So when you start moving that funnel, you start causing larger and larger amounts of variation. So I'd say in my experience, tampering is number one. People just constantly tweaking and playing, reacting to outputs without fundamentally understanding the cause. And we see this in services like processing insurance claims. We also see this in manufacturing, where there are managers quite often constantly making unauthorized or undocumented changes in how things are done, and collectively these can just cause chaos. Okay. So that's another source of what we would call a special cause variation, because people are just intervening in this process and changing it. And usually even they have big effects, and collectively it's often catastrophic after a while. Okay. So here's a simple example. So it's the same process. So they're machining these piston rings to get a final outside diameter. Notice we have our noise, but notice all of a sudden big upsets occur. Okay. And these big upsets, and I've exaggerated it only slightly, these big upsets have caused the process to change, and usually it requires intervention. So tampering refers to the case where the process is stable or it's in control, and we keep making adjustments based upon the outputs. And I call them superficial because they really don't get at the root causes. And so we just leave it alone. Special causes are going to typically require intervention. And the best strategy for special cause variation is to put in safeguards to prevent them from happening in the first place. Okay. And finally, I'll just talk a little bit about systematic variation. Um, Common and special cause variation are two common ways to describe variation in a process. But I like to discuss systematic because it has characteristics of both common cause and special cause. And the reason is systematic variation tends to be inherent to a system and it's persistent over time. Once you've characterized the systematic variation, okay, it's usually a large scale like special cause. The difference is it's predictable. Like seasonal trends in business, once people know them and characterize them, they're more or less predictable. So you always know you're going to sell a lot of product at Christmas, as an example, or you make something for the summer season, so you know you're going to sell a lot of product in the summer, and in the middle of winter you will sell very little. So once you've characterized it, you understand its presence, and then you may or may not try to do something to correct for it. So systematic variation, again, has the characteristics of common cause in that it's the source of it is always present, but like special cause, it often has a big effect. Here's an example. This is a process, and they're making some parts, and they're measuring the length of them, like metal rods. Notice that there's a pattern. This isn't random. This is constantly going up and down, up and down. This is not common cause variation, which should be just random noise. Something's at work. And usually what this signifies is you have two distributions. Where you see this, suppose this is a manufacturing operation and all the low readings, okay, as an example, let's see if I can. So the low readings, say, are the first shift, and the high readings are the second shift. So what you really have are two distributions mixed together, and with a little practice, you can see this. In fact, people often call this bimodal behavior because essentially, as you see on the next slide, there are two distributions mixed together. So again, it could be two different operators, two different shifts, two different machines, could be, two different people delivering a service, and so forth. Here's another example. Notice, in this case, the systematic behavior. Yeah, there's noise in here, but you can still see that systematic pattern. Okay. So sometimes the variation is seasonal. It is natural. There's nothing unusual going on. Okay, and here's a smoother picture of it. And this is typical of, for instance, if you were measuring daily temperature in many parts of the United States, where we have 4 seasons, this is what it would look like. Nothing unusual here, and you're either going to have to try to eliminate the effect. In many cases you can't, or you're going to have to figure out how to deal with it in a process. And I wanted to show one other example. So again, this is that piston ring example that you're looking at. But notice there's a pattern that develops somewhere around the 28th hour. What this is typically would indicate that the tool they're using is wearing out, so there's a systematic change in the process. Now this type of systematic variation, because we have some engineering control, they could, for instance, change the tool regularly, write an algorithm for the machine, some sort of computer code to constantly adjust the machine for tool wear, but there would be ways to deal with it. Okay? So here's an example, and this is, by the way, very typical of tool wear patterns. And in a manufacturing operation, as I said, you have to find ways to mitigate this because this would lead to unacceptably large amounts of variation. Okay, so basically some closing thoughts. Basically, the goal of a Six Sigma project is to, one, if the process is not stable, you need to get it to that point. You've got to get people to stop tampering. If there are sources of special cause variation, you need to find them and put in safeguards to prevent them. But our real goal is going after the inputs X, the common cause inputs that drive as 90, 94% of the variation. We're going to take stability or getting the process in a state of control as a given. But it is one of the first things you need to do as you enter the measure phase of the DMAIC process. Okay. And what this little symbol means is, let's call Y our measured output. It could be time to deliver a service, size of the piston ring, whatever we're measuring. And the output Y is a function of, and this is how they often show it in Six Sigma, of all of these inputs. So in Six Sigma, we're focused on these common cause inputs, and we're going to need some really nice statistical tools to try to figure out what those X's are. Essentially, they're the root causes of variation, and we need to find at least some of them that cause the bulk of the variation. The goal is to reduce variation. That means finding the common causes. Okay. That ends part 2 of understanding variation.